All right, so let's take a look at the three different types of symmetry for polar graphing. So the first one we're going to take a look at is symmetry across the polar axis, right? So polar axis, okay. You can see that in a scenario where something has symmetry there, that means that theta is going to be equal to negative theta. So just like we did with rectangular and symmetry, I'm going to go ahead and make a substitution and let, in this case, theta equal to negative theta. Okay, so let's go ahead and take a look at all this stuff for something basic. R equals sine theta. So here you can see that R equals to sine of negative theta, right? So there are kind of these properties that you can memorize for even and odd functions and all that kind of stuff. But remember, if you just look at the graph of sine, you can see that this graph right here, say I look at pi over 2 versus negative pi over 2, I can see right away here that they're not going to have the same corresponding y value. So right here, I can see that no, it's not going to have symmetry there. Right? The other types of, or two other types of symmetry we have are across theta equals to pi over 2, so the vertical axis there. So for this one, we can see that if we're talking about symmetry across that vertical axis, if this is theta, this would also be theta here, which means that this bigger angle would be pi minus theta, right? So I'm going to let theta equal to pi minus theta. Okay, so for this graph, or the equation we have is r equals to, and now it would be sine of pi minus theta. So we can go ahead and use the difference formula that we had from last chapter here. So this is going to come out to be sine pi cosine theta minus sine theta cosine pi. Right? And we know that sine of pi is going to be 0, so that first term really goes away. And I know that cosine of pi, so let's write 0 here. I know that cosine of pi is going to end up being -1. So this would be minus sine of theta times -1. So really this is just equal to sine of theta, right? So this thing, yes, it has symmetry across the pole. And that should make sense too, because we know that this is the graph of a circle that's tangent to the polar axis that is above the polar axis in between the first and second quadrants there, right? So that makes sense, right? The third and final type of symmetry that we're looking at here is for symmetry across the pole. So essentially it's across the origin and rectangular, right? So when we look for symmetry being existing across the pole, instead of thinking about like with rectangular where we substitute in negative x and negative y, really what we're looking at is we're going to have an r equal to negative r, right? So we're going to let r equal to negative r, right? So when we have that kind of set up there, remember, we're talking about symmetry here within the polar axis. So this is that circle idea. So here, if I go ahead and just have r equals to sine of theta, well, we know that r does not equal to, or negative sine theta is not equal to sine theta. So this is no on that, right? So it's not the same as the original function. So for this thing, we've established it does have symmetry across pi, theta equals pi over 2, which makes sense because this is the graph that looks like this approximately. Right? Well, it's a bad circle. But that's the basic idea. Okay, hope this helps.